I welcome you in this lecture on Plane T Junction. In the previous lecture, we have discussed Plane T Junction. So today we'll discuss Plane T Junction. As can be seen from figure 1, an Plane T junction basically is a three-port junction. Port number 1, 2, and then we have port 3. Ports 1 and 2 are collinear, and port 3 is in the side arm. Now from figure 2 we can see that the axis of this is the axis of side arm, and this is basically the axis of main waveguide. See, this is called as plane T because the direction of electric field, as we can see from port 1, the direction of electric field is along the axis of the side arm. Now say for example we consider TE10 mode, which is being fed at port 1. Now say for example this is port 1, and the direction of electric field for TE10 would be maximum at the center, and then it decreases towards the ends. So this is for TE10. So this is what I indicate here in figure 2. So the direction of electric field here, as can be seen, is along the direction of the axis of the side arm. This is the axis. So that's why it's called as plane T. Now let's see how is it formed. Let's see. Basically we have a waveguide. Let's assume we have a waveguide. This being our rectangular waveguide. So this is port 1, this is port 2. So what we do is that we cut a slot along the broader dimension of this rectangular waveguide. We cut a slot as is shown in this. This is the slot that we cut. Now after cutting the slot, we connect another section of waveguide like this. Let me use a different pen. So we connect another section of a waveguide over this slot. So this is what an plane T looks like. So along this broader dimension, we are cutting a slot and attaching another section of waveguide so that it becomes a three-port network. And this is basically how is it formed. So let me draw a cross-sectional view of this plane T junction. The cross-sectional view would look like this. This is port number 1, this is port number 2, and this is the port in the side arm. Ports 1 and 2, as I said, are collinear, and port 3 is in the side arm. Now so this is basically the same plane T junction. This is what I'm talking about. Now this is the cross-sectional view of this plane T junction. Now say for example I am feeding a TE10 mode at port 3. So what happens is that if I feed a TE10 mode here, the direction of electric field would be something like this. Now when it reaches this edge, fringing takes place, as in case of a parallel plate capacitor. Say for example we have a parallel plate capacitor with one plate being positive and other being negative at some point of time. Now what happens is that the lines of force would be from the positive plate to the negative plate. Now when we move towards the ends of these plates, these electric lines, they bend, which is called as fringing. Likewise here, in case of an E-plane T junction, what happens here is that fringing occurs. So this line is not a straight line like the other electric field lines, it is bent. So what happens is that on one side, say for example, I'll use the same color. This fringing is like this. So on one side, I have the lines downwards, the arrows point downwards, but on the other side or in the other arm, the arrows point upwards. That is the electric field direction. That is the field direction is upwards. Field direction is upwards, while here the field direction is downwards. So what it means is that the signals that come out of ports 2 and ports 1, they are out of phase, because at port 1 the electric field direction is upwards, while at port 2 the electric field direction is downwards. So this means with respect to port 3, the signal is coming out at ports 1 and ports 2 are 180 out of phase, or have a phase difference of 180 degrees. Now, in order to understand the various properties of this E-plane T junction, we need to find its scattering matrix. We need to find the scattering matrix. So from scattering matrix, we'll be able to understand few things. For example, if we feed a signal at port 3, it will come out, or it will be equally divided between ports 1 and 2. That is, half of the power will come out at port 1 and half of the power will come out at port 2. But the only difference in this case in comparison to an H-plane T would be that the signal is coming out of ports 1 and 2 would be 180 degree out of phase. And second thing that we can see is that in case of an H-plane T, we have seen that if we feed signals at ports 1 and ports 2, they simply add at port 3. But here it will be a phasor difference of the signals. Because of this 180 degree phase difference between ports 1 and 2, if I feed a signal at port 1 and another signal at port 2, the signal obtained at this port 3 would be a phasor difference of the two signals. Now, in order to determine the scattering matrix, we know that this is a 3-port junction basically. Let me zoom it. So, since it is a 3-port network, so naturally the scattering matrix would be a square matrix. Of order 3 cross 3. So for a 3-port network, the scattering matrix would be a 3 cross 3 matrix. Let me represent it as, so the elements of this S matrix would be S11, S12, S13, S21, S22, S23, S31, S32, S33. As we have already discussed the properties of scattering matrix, we have seen that for an n-port network, the order of the scattering matrix would be n cross n, and for a 3-port network, therefore, the order would be 3 cross 3. So this is a 3 cross 3 matrix. So our aim basically is to find these S parameters in order to find the various properties of this E-plane T junction. Now, another thing that we have seen is that the signal is coming out of ports 1 and 2 or 180 out of phase. If I feed a signal at port 3, I repeat, if I feed a signal at port 3, it comes out at ports 1 and ports 2 with a phase difference of 180 degrees. That means if this is port 1, this is port 2, and this is our port 3, S13 would be minus times S23, or S23 would be minus times S13. S23, because of this 180 out of phase or 180 phase difference, S23 would be minus S13. Further, if I feed a signal at port 3, let me draw it again. we have this as a 3-port junction. This is port 3, this is port 1, and this is port 2. Now if I feed a signal here at port 3, assuming this is the incident signal, then there would be a reflected signal B3. But this port 3 is matched to the junction. Port 3 is matched to the junction. So that means there are no reflections, which in turn would mean B3 is 0. That means basically S33 is 0. As S33 basically is B3 upon A3, and since it is perfectly matched, there won't be any reflected wave, there won't be any B3 in this case, so B3 would be 0, so S33 would be 0. Again, from symmetry property, because it is a symmetric network, if I draw here a plane, this completely bisects it. It looks symmetric with respect to this plane. So from that property, I can use symmetry property. From symmetry property, as we know, ijth element has to be same as jth element, or the transpose of the matrix is same. So that means S12 is same as S21. S13 is same as S31. Or for that matter, S23 is same as S32. Sij has to be same as Sji. So this means 1, 2 is same as 2, 1, 1, 3 is same as 3, 1, 2, 3 is same as 3, 2. So therefore, our S matrix can be written as, using these equations, using the above conditions that S12 is same as S21 and further S33 is 0, our S matrix can be written as S11, S12, S13, S12 because S21 is same as S12, S22, S13 is same as S31, S31 is same as S13, S232 is same as S13, and S33 is 0. Again, from unitary property. Now, if we look how many unknowns do we have? 1, 2, 3, 4. So we have 4 unknowns. So we need a minimum of 4 equations, 4 independent equations for determining these values. Now, again, from another property that is the unitary property. We know from unitary property, we know S into S conjugate is a unit matrix. That's for a lossless network, non-resistive or lossless network. The product of S matrix with its conjugate is a unit matrix. So that would mean, I'll write S as S11, S12, S13, S12, S22, S13, 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 0. I multiply it with its conjugate, which is S11 star. Star here represents the complex conjugate. Star, S12 star, S22 star, S13 star. Then S13, again S13 star, and then we have the third row, third column, S33 as 0, so would be its conjugate. So 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1. This is the unit matrix with diagonal elements as 1 and non-diagonal elements as 0. Now, as I said, in order to find these four unknowns, I need to have a minimum of four equations. So I'll multiply first row with first column, row 1 with column 1. So when I multiply row 1 with column 1, I'll get S11, S11 star. That would mean mod of S11 square. S12, S12 star would mean mod of S12 star. S13, S13 star would mean mod of S13 square is equal to 1. Now if I multiply, for example, row 2 with column 2, row 2 with column 2. So this is our row 2, this is our column 2. On multiplying it, I get S12, this S12 with this S12 star would be S12 magnitude of S12 square. S22 with S22 star would mean S22 square plus S13 star would mean S13 square. So let's name it as equation 1. Let's name it as equation 2. So I can multiply row 3 with column 3. Row 3 is this, column 3 is this. This is our row 3, this is our column 3. See, when I multiply row 1 with column 1, I get this diagonal element. Then on multiplying row 2 with column 2, I get the second diagonal element, which is 1. Now I am multiplying row 3 with column 3, I'll get this third diagonal element 1. So row 3 with column 3 would be S13 conjugate would be S13 square plus S13 conjugate would be S13 square, mod of S13 square. And 0 into 0 is 0. So this is equal to 1, this one. So let's name it as equation number 3. So from equation 3, this means 2 times S13 square is equal to 1, which means S13 is 1 upon root 2. So we are able to find S13. Out of the 4 unknowns, we have been able to find S13. So we are left with only 3 unknowns. So if I multiply row 3 in order to get the 4th equation, row 3 with column 1, I'll get row 3 with column 1. This is our row 3 and this is our column 1. So in this case, when I multiply row 3 with column 1, I'll get a non-diagonal element, which is all non-diagonal elements are 0. So I'll write it as row 3 with column 3 would mean S13, this S13, row 3, column 1 first element is S11 star, S11 star plus S13 into S12 star, S12 star. This time it will be 0. This is simple multiplication here, dot. So S13 can be taken as common. We are left with S11 star plus S12 star equal to 0. But we have seen, so the product of these two quantities is 0. Either S13 has to be 0 or S11 star plus S12 star is 0. But we have seen S13 is cannot be equal to 0 because S13 is 1 by root 2. So that means S11 conjugate plus S12 conjugate is equal to 0, which means S11 is equal to minus S12, or that means S11 is minus S12. Further, if we look at equations 1 and 2, on right hand side we have 1, on right hand side we have 1. On right hand side of both these equations we have 1. So their left hand sides must be equal. So that means I can equate the left hand sides of equations 1 and 2. That means S11 square plus S12 square plus S13 square is equal to S11 square 12 square 13 square is equal to S12 square plus S22 square plus S13 square. S12 square S12 square plus S22 square plus S13 square S13 square. So this and this will cancel out. So we are left with S11 square plus S12 square. This again S12 square and S12 square will cancel out. So we are left with S11 square is equal to S22 square. So that means S11 is same as S22. Now from equation 1 we know S11 square plus S12 square. Let me write it again. Equation 1 is S11 square plus S12 square plus S13 square is equal to 1. S13 as we know is 1 by root 2. We have already obtained its value somewhere. S13 is 1 by root 2 here. So S13 is 1 by root 2 square. Now S11 and S12 we have also seen here. We have seen this is what we have seen. S11 conjugate is minus S12 conjugate. So that means magnitude of S11 is same as magnitude of S12. So if S11 conjugate is minus S12 conjugate, that means their magnitude, the modulus, has to be same, which necessarily may not be correct for this thing. S11 may not always be equal to minus S12. So, but this equation holds valid. I had committed a mistake here. So, but this means S11 star is minus S12. This is the magnitudes have to be equal. So if I look at this equation now, S11 square, I can write it as S11 square. Magnitude of S12 is same as S11. Magnitude of S11 square plus 1 by root 2 square is equal to 1. So that means 2 times S11 square plus 1 over 2 is equal to 1, implies 2 times S11 square is equal to 1 minus 1 by 2 would be 1 by 2. This means S11 square is equal to 1 by 4, which means S11 is 1 upon 2. So this is our S11. So therefore from this equation S11 is 1 by 2 is S22. So this would be 1 by 2. Now I can write, basically I can write it differently. I can write it as, since we have written S12, instead of writing this, I can write S12 because this is basically S11 square. So instead of writing S11 as 1 by 2, I can write instead S12 square plus S12 square plus 1 over 2 is equal to 1. This is because we have seen above S11 magnitude. From this equation we have seen S11 is same as S12. So that's what I am writing here. S12 square plus S12 square plus 1 by 2. So 2 times S12 square plus 1 by 2 is equal to 1 implies 2 times S12 square is equal to 1 minus 1 over 2 would be 1 over 2. So that means S12 square is equal to 1 upon 4, which means S12 is 1 over 2. So S12 is 1 over 2. We have been able to find all these 4 unknowns. Therefore, I can write the S matrix as, S matrix would be 1 by 2, 1 by 2, 1 by root 2. 1 by 2, 1 by 2 minus 1 upon root 2. 1 upon root 2 minus 1 upon root 2, 0. We know that the reflected waves B, they are related to the incident waves A by this thing. So this is what I mean. If this is our H plane T junction, E plane T junction, this is our E plane T junction, we'll be having incident if it is port 1, this is port 2, this is port 3. Our incident wave here is at port 1 is A1. Our incident wave here is A2. The incident wave at port 3 is A3. And the reflected wave is, this is B1, this is B2, this is B3. So this is how the reflected waves shown in red colors are related to the incident waves shown in black colors here, A3, A3, A1, A2. So I can write it as B1, B is our B1, B2, B3. B1, B2, B3, the reflected waves are related by this S matrix, which is 1 by 2, 1 by 2, 1 by root 2, 1 by 2, 1 by 2, minus 1 by root 2, 1 upon root 2, minus 1 upon root 2, 0. And then the incident waves A1, A2, A3. So in equation form I can write it as B1 is half A1 half A2 plus 1 over root 2 A3. B2 is half A1 1 over 2 A1 half A2 half, I'm multiplying this by this, then minus 1 over root 2 A3, I'm multiplying this with this. Likewise our B3 would be 1 over root 2 A1 minus 1 over root 2 A2. Now let's discuss special cases. So case 1 would be A1 equal to A2 equal to 0, A3 not equal to 0. So that means A1 is this, A2 is this, and A3 is this. The first special case is we have assumed A1 is 0, A2 is 0, and A3 is not 0. This means we are feeding a signal at port 3, we are feeding signal here, and we are not feeding signals at ports 1 and 2. So let us see what happens. So we are feeding a signal, as I said, at port 3. That's what A3 is not equal to 0 means. So with these conditions, our B1 becomes, this B1 can be written as B1 is equal to half of A1 would be 0, half of A2 would be 0, and we have A3 by root 2, A3 by root 2. Likewise, our B2 would be half of A1 is 0, A2 is again 0, so we have the third element only. So B2 would be minus 1 over root 2 A3. Would be minus A3 over root 2. And our B3, which is 1 over root 2 A1, 1 over root 2 A2. Since A1, A2 are 0, so that means B3 is 0. So these are the three equations, three values that we get. What does it mean? Let's try to understand it. So that means if I am connecting a signal, if I am feeding a signal at port 3, it gets equally divided between ports 1 and ports 2, but with an introduction of a phase difference of 180. So you see B1 and B2, they are equal A3 by root 2, A3 by root 2. Only thing is that B2 is minus times B1, which in turn this means B2 is minus times B1. That means the phase difference between them is 180 degrees. So a signal being fed at port 3, gets equally divided into ports 1 and 2 with a phase difference of 180 degrees between the signals being obtained at ports 1 and ports 2. So power gets equally divided between ports 1 and ports 2. That's why it's called as a 3 dB splitter. 3 dB splitter. So that means if we are, say for example, feeding 2 watts power here, we receive 1 watt power at port 1 and we receive 1 watt power at port 2. So the power gets equally divided. Half of the power is being received at port 1 and half of the power is being received at port 2. That's why it is called as half power splitter or 3 dB splitter. Now let's consider special case second. Let me draw again the cross-sectional view of this plane T junction. This is our port 1, this is our port 2, and this is our port 3. Now in this case, again, this would represent an incident wave A1, A2. This is A1, this is A2, and the incident wave here will be represented by A3. Likewise, the reflected waves can be shown in red color as B1, B2, and B3. Now in this case, let us assume that A1 is equal to A2 is equal to A and A3 is equal to 0. So this means that two sources basically are connected. One is connected at port 1, another source is being connected at port 2, and we are not connecting or we are not feeding a signal at port 3. So that's what it means. A1 is equal to A2 is equal to A and A3 not equal to 0. We are not connecting any source at port 3. We are connecting sources at ports 1 and 2. Now let us see what happens to our equations. These B1 is 1 over root 2 A1, 1 over root 2 A2, etc. etc. We'll substitute these values in this set of equations. Therefore, on substituting, I'll get B1 as B1 would be simply A by 2. Let me write the equations first. So we know B1 is 1 over 2 A1, 1 over 2 A2, 1 over root 2 A3. B2 is 1 over 2 A1, 1 over 2 A2. This is what we have obtained, 1 over root 2 A3. And our B3, as we have seen, is 1 over root 2 A1 minus 1 over root 2 A2. 1 over root 2 A1 minus 1 over root 2 A2. Now with these conditions, let us write these equations now. B1 would be simply 1 over 2 A plus 1 over 2 A plus A3 is 0. And B2 would be, so this would be A by 2 plus A by 2 is A. B2 would be 1 over 2A plus 1 over 2A. That would again be A. And B3 would be 1 over root 2 A1 minus 1 over root 2 A2. So that would be 1 over root 2 A minus 1 over root 2 A. So that's 0. So that means if we are feeding two equal signals, A1 is A, A2 is A, at ports 1 and 2, we don't obtain anything at port 3. Power delivered to port 3 or power received at port 3 would be 0 if we are connecting two equal sources, as has been discussed in this special case. If we are connecting A and A, two A1 is A2 is A, this equation tells us. If we are connecting two sources with same signal strength at ports 1 and 2, the power received at port 3 would be 0. So this is simply acts as a difference. So at port 3 we are simply obtaining the difference of the two signals. So that's all for the day. Good day.